Hi, in this tutorial, I'm going to explain you how to model and optimize your inventory system. And we will do this in Arena software, which is a product of Rockwell company. Okay, once you open the Arena, such a window pops up. On the left side, you have the project bar, and there are different options that you can use in your modeling. Well, typically, I don't use any of these. Instead, I go to File, a Template Panel, Attach. I select Blocks, and then the Elements. Blocks and elements, these are really powerful couple to do your simulation. Well, if your model is not that sophisticated, you can use the basic process here or advanced process, but typically this block and element combination allows you to model literally everything that can fit into simulation context. So I'm starting with the blocks. We need to create the demand. So that's why I drag and drop the create rectangle into my workspace. And if you open this, it's asking you the batch size, first creation, entity type, interval. The most important thing here is interval. And I have my data. This means the interarrival time between the orders. So let me close this for a while and go to my Excel. Go to my Excel file. Here I have my sales data. 3rd of March 2018 at 05:15 I have sold 2 items. I have and 2nd of March at 18:32 I have sold one item, and so on. I have a data set of my past sales. So what is an interarrival time? That is the current order minus the previous one, or previous minus the current. So here it means that these are expressed in days, so 0.45 days, almost half a day between these two orders. I'm going to double click this. So all these numbers here, they are showing my interarrival time. This is my last order, this is the one before that, and they have been half a day between these orders. And the next one, I have only 1 minute in between these orders. That's almost 0.00 days. So what I'm going to do is, I need to know the distribution of these interarrival times. I'm just going to copy this into a text document. I'm going to call this as data set 1. I paste it to here and gonna save and close. And as you may know, Arena has Input Analyzer, a very useful tool that can tell you what distribution does these numbers come from. I'm going to use my existing data, and that is in Arena tutorial, and that's dataset 1. Here we go. They are here now. This might look like exponential or a Weibull. We don't know exactly, but if you go to fit all, you see that the distribution here is it's following gamma 0.697, and the second parameter of this distribution is 0.529, and the p-value is 0.09. Well, talking like statisticians, we say that we fail to reject the hypothesis that this underlying data is distributed with a gamma distribution with parameters 0.697 and 0.529. Okay, good to know this. Now we know that our interarrival times are distributed with such distribution. Now I'm going to go here and I'm going to write here the interval. That is gamma 0.697, 0.529, 0.529. Okay, let me just test this. If I click on dispose, it's running. Okay. So that's correct. Our interarrival time was distributed with gamma distribution. So the next thing to do is, I know now my order has arrived. Now I have to tell the model what is the demand pattern now. If I go back to my Excel file, I've counted these and I'm making an empirical distribution. I have 400 or 391 orders in this file. 375 of them is 1, 15 of them is 2, and only one order. In one order, I've got three different items ordered. So I can make this, I can explain this to my model. Okay, add. I'm going to make this demand, and the value is discrete 0.959. With this much of probability, the demand will be 1, and this goes cumulatively. So 0.997, the demand will be 2, and with probability 1, that will be less than or equal to 3. I click on OK here. Now my model knows the demand distribution and the interarrival times distribution. And what I usually do here is that I'm going to add to some animation. Okay, let's do that later. And from the elements, we need to declare the variables here also. In the blocks, I wrote here demand, so it needs to be in the variables list also. I need to define it. Okay, so demand is there. The demand is there. Now, I'm going to use branch. And in branch, I'm going to say if inventory level is greater than or equal to demand. Well, what happens if inventory level is greater than or equal to the demand? It means that I'm able to meet this demand. Otherwise, I lose the customer. So I will add else also. So two different options. Let us see now. I'm going to put another assign block here. If inventory level is greater than or equal to demand, I'm able to meet this demand. And I'm going to write here demand met. And I'm going to increment this every time by 1. So every time an entity passes through this block, it's going to increment it by 1. What else? I need to decrease my inventory level now. I've met the demand, and there is a decrease in my inventory level. Inventory level is equal to inventory level minus demand. Good. Okay, gonna click this one. And I will put another assign block here. No, it shouldn't be connected to this one. The connection will come from this branch. If I am not able to meet this demand, I'm going to count the lost orders. So I'm going to put here lost lost plus 1. Every time it will increment itself. I'm going to say OK. Good. I have now demand met. So I need to declare it in here also. Demand met. What else? I have inventory level. So I need to put it here also. And I've declared lost customers, the number of them. I'm going to say OK. Now, after meeting the demand, I need to explain the model, what's going to happen, because typically in our inventory models, we have SQ inventory policy. That means when the inventory levels drops below S, we order Q amount of Q units of that product. Every time this happens, we order Q of them. Every time we order Q units. Now, I have my demand met. I'm going to put another branch block here that will connect assign to here. If I meet the demand, then I need to check my inventory level. I need to check whether inventory level is less than or equal to reorder point. And I'm going to add else to here. So what happens if inventory level is less than or equal to reorder point after I meet a demand? So I need to order a new one, right? I need to increase my inventory. In this case, I'm going to put, again, one more assign block. If inventory level is less than or equal to reorder point, I'm going to say that inventory level is equal to current inventory level plus order amount. So what I mean by order amount, it's this Q. So back to our model. Now I have defined inventory level. I need to declare here reorder point and order amount. Now I have all these variables here. The last block should be disposed here. Otherwise, the entities will be collected in this system. Once I increase my inventory level, I let the entity to be disposed. I need to connect these also. These else also. Now, besides variables, I'm going to the elements. Here I need to explain how long I am going to simulate my system. My base time units are days, and I want to simulate this for 1 year, 365 days, and I want 1 month as warm-up period. During this warm-up period, Arena does not collect statistics. This is typically real thing, because when you start up a system, in the beginning, some noises or uncontrolled factors might affect your system, which will result in incorrect statistics. That's why it's a good practice to put some warm-up period to avoid those noises. I have my replicates here. Now there is one thing here. If we have a look at this portion where we say that inventory level is less than or equal to reorder point, I want to put some delay here because I have some machines. The inventory will not be increased in a second. It needs to take some time. Especially if I have my production area, I need some time to produce those, right? And that's gonna be done with delay element, delay block. So let me put my delay block here. And every time an entity arrives here, so I will produce this in batch, right? Because order amount, it will be like 10, 15, and each of them will take, for example, normal distribution 0.003 days with standard deviation 0.001. If I have 10 orders, 10 units to be produced, each of them will take a normal distribution 0.003 days on average, so I need to multiply these. I want some delay here to make it more realistic. Now I can connect my assign to dispose block. Now, if I want to make this more realistic, because I'm not working 24 hours in a day, and my working hours are from 8:00 to 17:00, 8 a.m., 5 p.m. Now, that's not visible here at the moment. I have to explain that to the model that if my order arrives in the late night, my inventory level drops below the below the reorder point, I need to make that order wait until the next day arrives. And that's going to be done with the scan block. Here I'm going to use some Arena variables that might or might not be familiar to you. Arena has its variables guide that comes for free when you download the software. Here you can find almost everything about how to define and how to use those variables in Arena. So one of those basic things is tNow variable. It shows the current simulation time. And my simulation time is measured in days at the moment. I open this scan block, my condition. So I want to explain the model that I am producing only between 8 a.m. and 5 p.m. Now this formula might seem a bit complicated to you, but I'm going to explain it in a while. tNow minus a int tNow multiplied by 24. This will be greater than or equal to 8, and the same expression should be less than or equal to 17. Let me open this again. tNow is simulation time, current simulation time. Let's assume that when the simulation is running, the current time will be 5.2 days. This formula, this aint, it removes the decimal part of this. So this function will give you 5. Now in my formula, where I say t now minus a int t now, that will give me 5.2 minus 5, which is equal to 0.2 days. So what I do next is I multiply this 0.2 by 24, which will give 4.8. So this means that the time is close to 5 a.m. in the morning. That's how I explain it. And I say that this number should be in between 8 and 17. And it's also a good practice to put a Q here, because scan block has its own internal queue also, but I usually prefer to define these as separate. Scan queue, okay, and then if I use a queue here, I need to define the queue here. I put queues element here, add scan queue. First in, first out, yeah, I don't have anything against that. Let's leave it as it is. And one more famous combination in Arena is seize, delay, and release combination. So if I have a machinery, the incoming entity is going to seize that resource, delay for some time, for production time, and then release it. So let me go to seize. I'll assume I have a machine. I'm going to call it as machine. And after some delay, I'm going to release that resource. Otherwise, if you don't release it, it will keep it occupied until the end of your simulation. So it's better to release it. So my machine quantity release is 1. I need to define this machine also in the elements. Okay, resources, and I'm going to call it as machine. Good. Now one last thing that I would like to change here is that this branch block. Now let's think of this theoretical case. One entity arrives, checks if the inventory level is less than or equal to reorder point, it's gonna come and wait in this queue until the morning arrives. Meanwhile, another order arrives, and again, it checks the inventory, still no production, it's gonna wait in this queue. Third one, fourth one, and then when the morning arrives, all these 4 or 5 entities will jump in, and that will create more production that I really want. So I need to put an extra constraints here. I'm going to open this. Okay, inventory level should be less than or equal to a reorder point. That is one thing, but I have other conditions also. And my machine should be free at that moment. And there should be no one waiting in the scan queue. So 3 components. Inventory level should be less than or equal to reorder point, and this my machine here, it should be free. If there is someone in, there is no point of sending that entity here. It will cause an extra production, which is not desirable at this setup. And then if there is someone waiting in this scan queue, either of these is satisfied, or both of them satisfied, then this path, the else path, will be chosen. Then now this should be fine. Let's run this model and see if some errors here. Invalid expression t now. There is, I'm gonna find and edit it. Some problems here. T now int t now multiplied by 24, and this parenthesis needs to be closed here. And the same problem here. Let's see what else is. Oh, seems no problem. If I click on yes, then the results will be displayed here. Not really useful statistics here. That's why the system number out, it's 0. Let's go to run setup. Default report should be some Simon summary report. I say okay. Let me run it again. Because I have not defined any statistics that I want to see, I need to do that. Okay, so I go to elements. I'm gonna put here dstats. Yes. What I want to see? I want to see the average value and maximum value of this lost. How many customers are lost? I want to see the average inventory level, for example. These should be the ones that are already defined in the variables. Now this should give me some results. Okay, at the end I'm losing 1019 customers, and on average this corresponds to 545, and the inventory level is 0. The average inventory level is 0 at the moment. For initialization, let's define some inventory level. At the beginning, let's assume we have 20 units in stock, and reorder point is 10, and order amount is 15. Or it means that when the inventory level drops to 10, I order 15 units. I say okay, and gonna run it again. Now in this case, I don't lose any customers. My average inventory level is 17.4, and this my machine utilization is 0.8%, and 60 times I have used the machine. As you can see, some more statistics are added into here, but what interests me more is the service level. That's the demand met over demand met plus lost. I'm going to dstats again and define this. Demand met over demand met plus lost. I need to put some +1 into here, because otherwise when the simulation starts, the demand met and lost, they are both 0, and the simulation model gives an error because division by 0 is not defined. So it doesn't really matter if I put this 1 here, but it will avoid that error. To avoid that error, now let's see what I've given here. Let's give a name to this one. Service level. This one is inventory level. And this is the lost customers. The simulation is run for 1 year. I use 30 days as warm-up period, so it's not calculated. Okay, in this case, the service level is 99.7%. My inventory level is 17, and again, the machine utilization is 0.8%, and so on. I can see as many statistics as I want here. But in this case, In this setup, I want to optimize my inventory. You see, I have two different parameters here, reorder point and order amount. I can play with these numbers, and typically companies are interested in low inventories. And I want to find what is my optimal reorder point and order amount. And that we do this with OptQuest. You go to Tools and open OptQuest for Arena. Let's save this first. I'm gonna save this in Arena tutorial and model 1. Okay, now go to Tools, OptQuest for Arena. OptQuest optimization. Controls. These are my possible controls. I'm interested in order amount and reorder point. I can give a low bound. It can be 1 and it can be as big as 50. And same as reorder point can be 1, between 1 and 50. And these are my controls. I want this model to play with these numbers and give me an optimal combination. And objectives, I right click and I want to add objective. What is my objective? I can go to responses. What is in here? Responses. The service level is here. I put a tick on this service level and an inventory level. Now going back to objectives, I want to minimize my inventory level while keeping my service level above 90%. I go to constraints, add expressions in service level. I want this to be greater than or equal to 0.9. I want to minimize my inventory as much as I can while keeping service level above 90%. That's a pretty fair and realistic example. Let's run this. Cannot start one errors and one warnings. No objective is defined. Okay, what's my objective? I need to put a click on this. The constraint is defined. Here we go. The system starts running. It's choosing different options, it's checking different values to find out what would be the optimal inventory level. Here the simulation, it's in a 1920s replication. Here it shows you graphically what is the current inventory level. We have dropped to 8 now at the moment. Well, as you see, the order amount, reorder point, these are decimals. I don't want this. I want to make them not continuous but integer. I'm gonna change this, and the step should be 1. Let's run this again to make it more realistic. Currently, with a reorder point of 10 and order amount of 15, my average inventory level will be 17, and this is feasible. It satisfies my conditions. However, we are looking for better solutions. Now it's dropped to 11. We have dropped to 7.75. It's now at 5.4. Reorder point 1, order amount 9. 8.1 seems to be a better solution. I'm gonna stop this when it reaches to, let's say, 75. So it's continuing. You see the development of the graph. I'm going to stop this at this point. Let's see, reorder point 1 and order amount 4 will give you 2.82 as average inventory. And this is what we are looking for. And this is an optimal solution. If I go back to my model and plug in these numbers, then it's going to give me exactly the same, this 2.82 as average inventory level. Let's save this. And I'm going to compare this. This is one approach. I have inter-arrival times, and then I have the demand distribution, where I can plug in and I can assign the demand distribution and check how this system behaves. Now, another option is to aggregate those weekly. Well, as you see, typically normal distribution is used in the literature to model these inventories. So we mainly assume that the demand during inter-arrival time or demand during the lead time is normally distributed with some mean and standard deviation. Let's do the same and check. It's exactly the same model. Instead of putting the inter-arrival times and empirical distribution for my demand, I'm going to use normal distribution. And I've copied these and weekly aggregated weekly. And this is my last 54 weeks data. In each week, how many total sales I have realized. And if I draw this, the histogram, it's gonna be normally distributed. So we can do that, but it doesn't matter if you have more than 30 data. According to central limit theorem, it can be assumed that this distribution is normal. But let's check. We go to analysis diagrams, histogram, or analysis diagram. Yeah, histogram, and my data is here. I click on next and finish. The Kolmogorov-Smirnov test p-value is 0.34, which is pretty high. So we fail to reject that this demand distribution is normal, and the mean and standard deviation are given here. I'm going to open the model, which is exactly the same model, but a different approach. With a different approach with weekly arrivals which follow normal distribution. This is the same model, but I have here the weekly arrivals, and I assume I assign the demand as normal 1910. Let's run this model and see what happens. Here the service level, it's 0.74. The inventory level is 32. So if I want to maximize or optimize this one also, I go to OptQuest. By the way, if you want to animate this arena, we do one more thing. You drag and drop pictures element. I put here picture.redBall. And then you come to assign block and put entity.picture is equal to picture.redBall. And then it starts animating the thing. Okay, here the model is already built and the conditions are same. I want my service level to be above 90% and I want to decrease my inventory level. This one started with an infeasible solution and then jumped into a feasible one. Currently, it's 43 with order amount of 29 with reorder point of 29, the same. It's searching for better solutions. Let's see. Let's wait for some more applications. Remember, in the previous model, our average inventory level was below 10. Now, in this case, at the moment, it's 39. It's now running 45th replication with it's currently these the order amount of 33 and reorder point of 23 will yield average inventory level of around 40. So exactly the same problem, but two different approaches. They yield totally different values. This, in the second one, where I assume normal distribution, the average inventory level is almost 5-6 times higher than the one when I assume better inter-arrival times and discrete demand distributions. So here in this example, we discussed how to model inventory in Arena, and then we showed that there are several ways. There might be several ways to model this exactly the same model, and they might yield different average inventory levels and also different costs. Thank you for listening and watching this video.